again. Welcome back after the coffee break. Hope that you had a lot of coffee and a lot of cakes. I think that we have here a great topic to delve in. We're talking a bit about the brave new world about wood extractives, which is very interesting because typically we don't tend to focus that much on this type of components of wood. And I remember the last session we talked a bit about the lignin, and in the industry we have a saying that you can do anything with lignin except money. I think that on extractive fronts we have now 3 chances to prove that the extractives actually have a value and can create more money for the industry as well. So, having said that, we'll start with Ricardo Costa. So Ricardo Costa is a PhD student of Forestry and Natural Resources from Centro de Estudos Florestais and Instituto Superior de Agronomia. He took the bachelor and master's degree in forest engineering and natural resources in the same university. And he's developed his work in lignin extraction and nanoparticles production for value-added products. So he's going to present the work, lipophilic extracts from eucalypt and acacia biomass, valorization route under the biorefining context. So, Ricardo?
So, good morning everyone. Thank you, Mr. Chairman, for the kind introduction. So, where I bring you today is the lipophilic extract from eucalypt and acacia biomass, a valorization route under the biorefining context. And in this presentation, I will make a brief introduction about the biomass that we used of eucalyptus and acacia, the objectives, the methodology, the results, and some final considerations. And starting with the eucalyptus, so we used eucalyptus stumps from Eucalyptus globulus, and the stumps are the basal part of the tree that stay in the ground after the full cut down of the stands, and after each revolution they need to be removed from the soil for the new installation of the new stands. And they can represent up to 5 tons of stumps per hectare. These stumps are either used for the incorporation in the soil for nutrients for the new trees, burned to produce energy, or nowadays they are already being used by the industry on the incorporation of the wood pulp production system. However, they have the potential to be further valorized before this final outcome. Moving on to the acacia, we used residues from Acacia melanoxylon, and acacia species in Portugal are considered invasive. They are dominant over native species and have a rapid proliferation due to especially after forest fires, and leads to losses of biodiversity and habitats. Control operations are mainly mechanical, which include, for example, the debarking of the tree at breast height, which will eventually lead to the death of the tree, or the clear cut of the trees and the application of a biological control to prevent the copy sprouting. However, these operations are very costly and stakeholders don't get any return from them, so they don't have any incentive to do these control operations. So every year the invasiveness of acacia species worsens. And so the objective of the work that I'm presenting is, in the case of the stumps of eucalyptus, is to further valorize its potential before the application, the final outcome. And in the case of acacia, is for stakeholders to have an outcome and minimize the costs of control operations. And the first thing that we can do with biomass, and without affecting the structural components, is the removal of the extractives with solvents of different polarities, and to identify those compounds and see if we have interesting compounds to apply in a use. In this work, I will present some interesting compounds that we found on the dichloromethane extract, which is a non-polar solvent. And so the raw material that we used were stumps donated by ALTRI. We separated the bark from the woods and we analyzed separately. And in the case of acacia melanoxylon, we went to Parques de Sintra and Monte da Lua, and they have two piles, one of wood chips and another one of crown residues, which are mainly composed of branches and leaves. So we took to the lab, we grinded below 2 millimeter particle size, and we extracted with dichloromethane by Soxley extractions, and we analyzed it by GCMS. And so, moving on to the results of Eucalyptus globulus, here we have the full chemical composition of stump and bark. I don't know if you can see well, but we have in light blue the polysaccharides, in green the lignin, the red extractives, and the grayish the ash contents. And they have a very similarly chemical composition, and we are interested in the extractive fractions, which are mainly composed by extractive soluble in ethanol and water, as you can see with the light blue and green color. And the ones that we analyzed here were the ones in dichloromethane, which represents only around 0.7% of all biomass. I know that this is really a low amount, but our idea is to extract all the components soluble in different types of solvents and to see if we have interesting compounds to use it in a valorization route. So, moving on to the identification of the extractive soluble in the dichloromethane, here we have a graph of the families of the compounds identified in the case of the stumps, bark and stumps woods. We have mostly fatty acids, sterols, and triterpenoids. And the ones that are most interesting are the sterols and triterpenoids, because the other ones are fairly easy to obtain from other sources. And what I will show you after is 4 compounds that we found in the dichloromethane extract of stumps from Eucalyptus globulus that have interesting properties in the medical field. These compounds were only assessed in the lab, so they are not used already, of course. But first compound we have is beta-citosterol, which has properties of anti-inflammatory, carcinogen, and a cholesterol inhibitor. And in the case of the stump bark, we can get up to around 1,700 milligrams of beta-citosterol per kilogram of bark and 900 milligrams of chips per beta-citosterol per kilogram of chips. And because the economical part is very important to scale up a lab, so 10 milligrams of this extract on Merck is around 300 euros. So another compound is the 3-acetylursalic acid, which has only an anti-carcinogenic properties and was only found on stump bark with 800 milligrams per kilogram of bark and around 400 euros of 10 milligrams of compounds. Another one is asiatic acid, which has anti-inflammatory, neuroprotective, or anti-carcinogen activities, only found in this case in chips and with roughly 350 milligrams per kilogram of chips. And the last one in the case of the stumps is arsenolic acid, which has some antioxidant properties, heart protection, and cholesterol inhibitor, with only found on chips, 300 milligrams of arsenolic acid per kilogram of chips, and with around 3,000 euros per 10 milligrams of these compounds. I am showing you only 4 compounds because these were the main ones that we found, with highest amounts. There are also other compounds that were interesting, but either were in very low amounts. But doing an extraction, we can always decide the retention time to get those compounds, purify it, and use every compound that we think that it's interesting for an end use. Moving on to the acacia melanoxidant biomass, we have the chips and the crown residues. These ones have different chemical composition, with chips having more cellulose than crown and less lignin, and with a little bit of more extractive content than the eucalyptus. But of course, it's also, most of them are soluble in ethanol and water. But in the case of the crown, we can get a little bit more, around 2% of the whole biomass. Moving on to the families of these compounds, we have mostly the same families: fatty acids, in this case also alkanols for the crown residues, sterols, and caffeates. Again, the only compounds that are mostly interesting are the sterols and triterpenoids. And the first one is alpha-spinosterol with anti-inflammatory activity, anti-tumor, and anti-diabetes, found in both chips and crown, and with crown residues having about 1,200 milligrams of these compounds per kilogram of crown residues. Another one is beta-acetosterol that we had already seen in the stump residues, with 460 milligrams per kilogram of chips and 500 milligrams per kilogram of crown residues. Lupiol is another one very interesting, with antioxidant wound healing properties, anti-protozoal and antimicrobial, only found in the crown residues with around 500 milligrams per kilogram of chips. Beta-amyrin with anti-inflammatory, gastroprotective, and antinociceptive activities. Antinociceptives is the properties that a compound has to relieve pain without affecting our consciousness. And we have 375 milligrams per kilogram of crown residues. And lastly, we have betulinic acid with antiretroviral properties, anti-carcinogen, and anti-malarial properties, found in both chips and crown, with around 150 milligrams of kilogram of chips and 250 milligrams per kilogram of crown residues. And some final considerations. So, extract is soluble in dechloromethane, have a huge potential to be used in the industry, and it's really important that for the acacia residues, it's only for the outcome for stakeholders to have an income to do control operations actions to prevent the further spreading of the acacia biomass. What we will do later is the identification of the compounds soluble in ethanol and water, which are mostly the compounds found in this biomass, and we will have further valorization rounds for these compounds. So I want to acknowledge all the funding that we have, all my co-workers that work with me every day, and thank you for your attention.
Thank you, Ricardo, for a very nice presentation and for the nice timekeeping. Makes my life a whole lot easier. So next presentation is going to be the title, Advances in the Recovery of High Value Added Compounds from Acid Sulfide Pulp Production Streams, from Dmitry Evtyugin. So Dmitry is graduated in Pharmaceutical Sciences from the Faculty of Pharmacy, University of Porto. After working as a pharmacist for several years, in 2018 he joined CISECO research group at Innovator University, working on utilization of sulfite liquors in collaboration with industrial partner. You don't need to guess who. He's currently a PhD student in biochemistry, Department of Chemistry at University of Aveiro. He's the author of 6 publications in peer-reviewed journals, 2 conference papers, 2 patents. His main scientific interests include polyphenolic compounds and sterols, their bioactive properties and possible applications, pharmaceutical, cosmetic, food, and technical areas. So, Dmitry, welcome.
Thank you, Mr. Chairman. Good morning to you all. And firstly, I would like to give special thanks to the Committee of Tecnicelpa for giving me this opportunity to get to share with you a part of my PhD work carried out in collaboration with CAIMA Pulp Corp and entitled, in this case, Advances in Recovery of High Added Value Compounds from Acid Sulphite Pulp Production Streams. As we all know, sulphite pulping is the second most important cooking process after craft, and is the only one that deals with the lignification of wood under acidic medium. This feature largely predetermines not only the possibility of achieving easily bleachable pulp, but also to use byproducts that are dissolved in spent liquor, among which little is known about possible bioactive compounds. Meanwhile, in dissolving eucalyptus pulp, we find around 85% of extractives dissolved in sulfite spent liquor, and the other 15% will then be subjugated to the further bleaching steps. Among these extractables, some paradigmatic bioactive compounds such as ellagic acid and sterol-based products can be found in abundance, and thus can be recovered from both the sulfite spent liquor and the alkaline extract from the first bleaching stages. However, no industrially viable processes have yet been proposed, and hence the main objective of this project was to develop industrially viable and technologically possible ways to recover these compounds. Now, why we have selected these effluents? This dates back to our previous work when we analyzed the major extractives in the sulfate pulp line and concluded that ellagic acid can be found in both effluents and the pulp. It should be noted that ellagic acid can be adsorbed on pulp and then extracted during the extraction stage, and thus it was proposed that in spite of being present in great quantities in the spent liquor, it can also be present in the effluents from the alkaline extraction stage. In terms of sterols, they follow a relatively similar profile. However, during cooking, the conjugated sterols are hydrolyzed, and thus why we have a higher amount of free sterols in the pulp than in the original wood. The sterols are also easily leached during this extraction phase, and thus we concluded that they also can be present in the alkaline extracts. Now, why we ought to have an interest in these products? Well, in case of ellagic acid, it belongs to the polyphenols known as ellagitannins. It can exist in its free form, as presented in the structure, or as a part of the more complex structures, the ellagitannins themselves, but which can give rise to ellagic acid under acidic or basic conditions. Eucalyptus globulus can be considered a very good source of ellagic acid, ranging around 1 gram per kilo. The same can be said about some of the ellagitannins, such as castalogin and vescalogin. Ellagic acid has been gaining popularity, especially in food, cosmetic, and some technological areas, mainly because of its antioxidant capabilities and also a very unique planar structure. The plant sterols are cholesterol-like molecules that exist in plants, being cytosterol, as already been taught, the most representative. It is also the most abundant sterol in Eucalyptus genus. Phytosterol-based products can have a wide range of uses, ranging from hypercholesterolemia control to prostate supplements, to selective replacements for fat matrices in functional foods, or even as raw materials for the production of steroid-based drugs. In case of Eucalyptus globulus, we can consider it also a very good source, especially if the conjugated sterols are hydrolyzed, and there we will reach more than 1 gram per kilo also. The principle of the proposed recovery for the ellagic acid lies in its reduced solubility under its pKa values and the high tendency to crystallize under favorable conditions. In practical terms, this means that there is a formation of ellagic acid crystals at natural pH of the liquor, around 2 and 3. This is with predefined temperatures and times. As such, we could observe that when we expose the liquor, there is a partial precipitation of the ellagic acid that mostly occurs in contact with the surface material. In this context, the phenomenon that takes place, we could call it nucleation, as in the formation of inductive nuclei that will promote the formation of crystals at the surface of the material. These crystals then can be easily separated by filtration or centrifugation. As such, kinetics of the precipitation of ellagic acids were evaluated in recipients with the same surface to volume area and at 6 and 20 degrees. In this case, the most important finding was that more than 2/3 of the total maximum content was reached within the first 72 hours. Additionally, in spite of the total content being high at 6 degrees, the 20 degrees presented the higher purity. This preliminary test has allowed to conclude that temperature is in fact a key factor in the recovery of this compound. Thus, we made another experiment, in this case, studying the influence of temperatures up to 90 degrees. And we can conclude that the highest total content was achieved around 80 degrees. Now, why is that? It has a simple explanation, because with the temperature, the solubility of impurities increase. And thus, there is more freedom for the rearrangements of ellagic acid molecules to form crystals. However, when we are approaching boiling points, the solubility of ellagic acid increases, as well as the fluctuations in the near wall space, and thus reducing the ability to crystallize. Additionally, in this experiment, we tested for the first time the possible successive washings with water. And as you can see, we concluded that the successive water washings can drastically increase the purity of the product. I was talking about surface to volume ratio. In fact, we made another experiment searching for an understanding about its influence on the recovery of ellagic acid. As we can see, even small differences in S/V ratio favor the crystallization of ellagic acid over time. At the same time, we can see that we made another experiment with a large series of containers with different S/V ratios and concluded that there is a logarithmic dependence, once again pointing out that for the same volume of the effluent, with higher S/V ratios, we have a higher content in our product. Finally, we've made another experiment on the influence of the surface material and the deposition of ellagic acid. Interestingly, we studied borosilicate glass, stainless steel, HDPE, and PET. And incredibly, is precisely in the stainless steel when we had the most content. However, the purity was found mostly for the polymeric materials, being maximum in HDPE. Why is that? Again, because of the nucleation effect. There's more affinity between the material and the ellagic acid. However, it should be pointed out that inox had another peculiar problem. It clings too much to the material. And thus, it is very challenging for the next steps. Aside of that, inox was also the one when we saw more concomitants. Thus, we conclude that polymeric materials would be the best choice. Additionally, we made a study on the concomitants, on their nature and on their proportion, as well as the first, this is the second test in an alternative washing protocol. This is with acidified water. And we found that among concomitants, the most abundant that we can see are the lignin, the aldonic acids, followed by lipophilic extractives, and then the various mineral and organic salts. The washings actually show that it's possible to drastically remove some of these components, especially carbohydrates and mineral and organic salts. Why I'm talking about the latter ones? Because the removal of heavy metals can be especially important for food or biomedical applications, as we will see later on. The purity confirmation was mostly made by gas chromatography mass spectrometry with calibration of an ellagic acid standard, and this led us to confirm that it's actually possible to achieve purities above 90%. At the same time, we made solid-state carbon analysis and X-ray diffraction studies. we can see that there are unquestionable similarities. However, there are some differences that can be justified by the fact that the crystalline structure is highly dependent on the impurities and the degree of hydration. Additionally, there are inherent polymorphism for the crystalline structure itself. However, we can see that during the crystallographic analysis, we could see many similarities between the crystalline planes, between the standard and our product, thus confirming its purity. Additionally, we hypothesized that pore morphology of the container material influences the orientation and the formation of ellagic acid crystals, as well the concomitants and possible metallic complexes. And now talking about metals, one of the most crucial aspects for the final product to go into the market lies within the safety levels for the organic solvents and the heavy metals, mainly the big four, the mercury, the lead, the arsenic, and the cadmium. As we can see with the comparison from the European guidelines for food additives, we made an example for the curcumin, which is a well-known natural antioxidant. And as we can see, we already achieved, through those successive acidified water washings, a sample that is within the safety limits. The sterile recovery was developed from the alkaline extract from the first bleaching stage and involves a first neutralization at pH 7 immediately after the recovery of the effluent. Why? Because we want to avoid the degradation of our main products. Later on, we have two more adjustments in pH, one to pH 5 and another to pH 3, with the subsequent separations of the sediments. The latter adjustment warrants that we should extract this sediment with several times with methanol. And this organic phase is then going to be used to add some water, a small quantity, which causes the precipitation of the sterols, which then can be easily separated by filtration or centrifugation. And after drying, we have discovered that actually, for the most of our samples, there is a common trend of having above 90% in cetosterol. The choice of the organic solvent and the addition of water are the key elements to this process. And now, why using methanol? In spite of methanol having a less solubility, the cetosterol has less solubility in methanol than in other types of our selected organic solvents. However, the methanol gives a room for selectivity because some of the other lipids, such as, for example, the sterile conjugates or the triacylglycerides, they are sparingly soluble in methanol, and thus the methanol was considered to be the best choice. When adjusting the pH to 5, there is a possibility of intermediary products, one of which is ellagic acid, which we expected, and the other, surprisingly, was high crystallinity cellulose, which by the NMR and the XRD studies was found to be beta cellulose. This intermediary step was found to be actually important for making the further methanolic extract with less impurities and thus contributing to the purity of the final product. Now, the recovery of ellagic acid was much lower than that we expected, and much lower, especially when we consider the sulphite spent liquor. However, it was still an important intermediary step, as I said earlier, because it would allow us, not only it does not have any interference, it can actually aid in achieving higher purity of the final product. Interestingly, if we change the organic solvent, for example, to ethanol, the main product will be mainly constituted by conjugated sterols. And in this case, we found that the average yield for free and conjugated sterols is around 0.21 and 0.27 gram per liter, respectively. It should be noted that these products, the conjugated sterols, are on the market, are produced synthetically by the esterification of free sterols. In conclusion, we can say that high-added value compounds such as ellagic acid and citosterol can be readily recovered from industrial streams of sulphite pulping, such as sulphite spent liquor and/or alkaline extract from bleaching stage, using sustainable approaches. Ellagic acid is recovered via selective crystallization from the spent liquor, with the yields up to 0.44 grams and the purities up to 95%. Beta-citosterol can be recovered from the alkaline extract by two-step acidification to pH 5 and 3 and under preselected conditions. And it's possible to reach yields of 0.21 grams and above 90% of purity. The extra profits for the industrial mill, for the sulphite industrial mill, could reach above 100 million for the ellagic acid alone. Thank you for your attention, and special thanks to CAIMA and Universidade de Aveiro.
Thank you, Dmitry, for a very nice presentation, very nice conclusions. And now we put a value tag on the value, which is 120 million of potential. So final but not least, we have a final presentation from a work called Chemical Composition of Cuticular Waxes and Cutin in Eucalyptus globulus leaves. This work is going to be presented by Professor Helena Pereira from Centro de Estudos Florestais do ISA.
Good morning, everyone. It's a pleasure to be here. As you see, it is not Rita Simões who is presenting this work. She is an early stage researcher. In fact, she was the one who did all the experimental work, but she could not make it, so I am presenting the work. We are located in the Forest Research Center, Centro de Estudos Florestais, at the School of Agriculture, Instituto Superior de Agronomia of the University of Lisbon. And in this research center, we have for many years devoted our research to forests and to forest products. One of our research lines is related to the part of the trees or of the plants that are barriers with the environment. We started many years ago working and researching on barks with a special interest on cork, and after that in cork-rich barks. And now, recently, we are devoting our interest to another barrier, which is located in the leaves. So the skin of the leaves, the cuticle, and this is the work I am going to present here. These barriers are chemically very interesting. So, in addition to the physiological role they have also an enormous potential of valorization by chemical routes. So, well, our work, in fact, with the leaves and the cuticle of leaves started with the cork oak. This was the theme of Rita's PhD work, was related to the cork oak. And we are enlarging the scope, and of course, we had to start with Eucalyptus globulus leaves. There are very few works already on that, 3 to 4 papers, but they failed to quantify the cuticles and to address the chemical composition specific to each component. The leaves are, in fact, covered by an external skin, an extracellular membrane of soluble and insoluble lipids. And this cuticle has an important physiological role, an environmental role, because it regulates the non-stomatal water loss of the plant and the gas exchange, and also the interaction and the resistance to several biotic and abiotic stresses. So, as these two functions allow us to think, they have a potential important role addressing changing and adverse environmental conditions. Well, we have in this cuticle, we have an insoluble polymer, the CUTIN, which is a glyceridic polyester, a bit similar to suberin, which is a matrix of hydroxy fatty acids, mostly with 16 or 18 carbon in the chain. And also, a very important component are what is called the cuticular waxes. And these cuticular waxes, they are soluble in low polarity solvents, and they consist of two parts. One is are the waxes that are embedded in the cutin. They are called the intracuticular waxes. And the other one is on the surface, is the surface layer, and they are called the epicuticular waxes. And they include several compounds and several chemical classes, but mainly triterpenoids and long-chain aliphatic acids. Given the objective of this session, we are focusing in the objectives about the valorization of the leaves. Both, and we considered both juvenile and adult leaves of Eucalyptus globulus. And of course, for that, we have to determine content in waxes and cutin and their chemical characterization. Of course, in addition to these objectives, there is an underlying objective of knowing more about this barrier to the environment and the physiological role that eucalyptus leaves may have through the cuticle. We have some methodological challenges. We are not isolating the cuticle. This is very a high workload. So we are extracting the waxes and the cutin in all leaves. Well, the leaves of eucalyptus are rather big, so they would not fit in the usual vessels that we had. So we had to adopt a sort of soft extraction method using flat glass vessels. And we did a very short time extraction to extract the epicuticular waxes, and then a longer, a 3-hour extraction near boiling point of the solvent, which was the dichloromethane, to extract the intracuticular waxes. Then we wanted also to characterize the cutin. And the cutin, for that, we need a reaction, a transesterification reaction, and we need to put the leaves into the vessel. So we had to cut them. So in order not to contaminate the composition of the cutin, we cut the leaves, we shredded them, and made a further extraction to extract all the compounds that were soluble in the dichloromethane. And we call them the internal DCM solubles. And of course, we quantified the yields, and we studied the composition by GCMS analysis. We had some surprises. With our knowledge of what happened with corcoke and some other species we already studied, we had some surprises. First, let me call attention to one point, is the two ways of quantifying the amounts. One is the normal mass content. So grams or milligrams per gram of dry material, or percentage, as we always use. And another way is to quantify what is called the leaf surface coverage. So how much is covered per unit area of the surface. So this is then the amount per square centimeter of surface. Well, what did we find? Let's first talk about mass content, which is the unit most important for valorization. So amount per amount of raw material. Epicuticular waxes amount to 2%, more or less, of the leaves. Juvenile and adult leaves are similar. Intracuticular waxes amount to 3 to 4%. Also rather similar between juvenile and adult leaves. So that means that in this mass content, the total waxes are between 5 and 6%, which is a considerable amount. Then these internal DCM solubles, also similar between adult and juvenile leaves, and they amount to 4%. Still, also a considerable amount. But then the surprising thing is the CUTIN. CUTIN represents, again, similar in juvenile and adult leaves, is about 16%, which is rather a lot. If we now consider this coverage, surface coverage, and this is one of the surprises in our study, is that we have a very first, juvenile and adult leaves are different, and we have a much higher coverage in adult leaves. For instance, you see there the total cuticular waxes. They are 350 micrograms per square centimeter in juvenile and 650 in adult leaves. This is a lot. This is, for instance, about 3 times what happens in the cork-oak leaves. So this means that eucalyptus leaves are very well protected by these cuticular waxes. And also CUTIN is a lot. So CUTIN gives a sort of mechanical, physical resistance to the leaves. So that means that also from this surface coverage, the eucalyptus leaves are well, are resistant. And this, of course, can be, is useful when addressing their resistance to environment, to changing conditions, to biotic attacks, and so on. Then composition. Again, we found that juvenile and adult leaves were rather similar. Most of the compounds of the epicuticular, intracuticular, and these internal DCM solubles were mostly made up by terpenoid compounds. You see these 3 big bars, they are the 3 terpenoids. Both the fatty acids, the alkanols, the sterols, and so on, they were present, of course, but in very much smaller amounts. The same happened in adult leaves. So terpenes are the compounds that are dominant in this system. And in that composition, of course, we have the full composition, but one compound strikes out, which is ursolic acid. And this appears both in the epicuticular waxes, in intracuticular waxes, and in these internal DCM solubles. And similar in juvenile and adult leaves, and it amounts, you see the different values, about half. Half of the extract is ursolic acid. And ursolic acid is a rather interesting compound with a lot of potential bioactivities. So we were very, very enthusiastic about these findings. Then, of course, CUTIN. CUTIN is a polymeric structure. We have to depolymerize it, and we studied the monomers. One monomer is glycerol, which is the connection between the long-chain monomers and the long-chain monomers, and they are dominated by hydroxy acids. Again, similar in juvenile and adult leaves. And in these hydroxy acids, they are dominated mainly by 3 acids, hydroxy acids, with 18 carbons, with a mid-chain functionalization, both a double bond, an epoxide, and a dihydroxyl functionalization. So this together, they make up about 70% of the total. So this is again an interesting find, finding with these functionalized compounds that can be used further in chemical pathways. So this, I'm finishing. So our final considerations. Of course, we were also happy to have developed this methodology of analysis. We found that this mass content of WOXes and CUTIN was similar in juvenile and adult leaves, which is practical when you are valorizing the material, but the surface coverage is much higher in adult leaves, which gives these leaves in adult eucalypt trees a very much high resistance towards water loss, therefore draft events and so on, and biotic resistance. Ursoleic acid was a major compound. The CUTIN content was very high and had this mid-chain functionalized hydroxy acids. So this led us to consider that Eucalyptus globulus leaves could be a source of chemical compounds in addition to what we are already using them for, which is essential oils. Well, I have to finish by thanking the funding structures, and it was FCT who funded or funds our research center and the PhD fellowship of Rita. You have our emails. If you have further questions, we can always contact by mail, and thank you very much.
Thank you very much for a very interesting presentation, very insightful. I think now we have the time to 10 minutes of questions, and luckily we have 3 topics which tackle similar type of components, probably with the exception of ellagic acid. So any questions from the audience?
Yeah, thanks for your presentation, very interesting. So regarding the content of CUTIN and terpenes in eucalyptus, you showed somehow like the composition in leaves. For example, 16% of CUTIN. Do you have an idea of the composition based on kilogram or ton of wood of CUTIN?
Okay, sorry. When we are talking about CUTIN, we are talking about leaves, not about wood. So the CUTIN is on the leaves, and yes, we have the mass percentage. WOXes amount to 5 to 6% of the dry matter, the leaves dry matter, and CUTIN to 16%. So, for instance, for WOXes, if you consider that about half of the extract is ursolic acid, that means that we have about 2%, well, theoretically, 2% of ursolic acid from the leaves.
Thank you.
Paula here.
Thank you. Thank you for your nice presentation. The question is for CUTIN as well. What kind of applications that you foreseen for CUTIN and the type of extraction process that could be scaled up for applications?
Yeah. Thanks for the question. So that allows me to develop a bit further a potential valorization pathway. Well, leaves, they are already collected, for instance, for extraction of essential oils. So they are already available in these, well, not very big sites, but they are already available. And they can be collected at the time of harvest, not very difficult. So if we have a possibility of extracting them whole leaves, like we did here, with these rather big amounts, that is an easy way of extracting the oxys. Ursolic acid, you have seen, and it is reported that it has bioactivities. Some of them possibly interesting medicinal properties. Of course, it is a pathway to valorize it towards medicinal uses, but maybe an easier way would be to go to nutraceuticals applications, which are less regulated. Of course, we have to purify, and this will be our next job, is to come with this raw extract and purify it into our, a bit like you did in your materials, to purify it. One advantage is that it is a major component already. So 60% or more than 50% is already there. So that's interesting. Of course, afterwards, in this full resource use, we should also valorize what is left. And there are different ways, but already a good way is to make, for instance, thermochemical, to use the thermochemical pathway to make, for instance, biochar or whatever of the leaves. Yeah, so it is an interesting, and we are just beginning. We are very much astonished about our results, and let us not forget the potential of doing further work, of looking, for instance, genetic differences on this cuticle, and geographical differences, and so on. So looking at the environment-plant interaction.
Very good. Any further questions? While people are thinking, I'll probably shoot a couple of questions here to thrive the discussion amongst the other guests. So I'll throw two questions to Ricardo. So one more specific. So I noticed that on the quantification of the extractives, you have quantified about 10% extractives on the material, which for the people in the industry is a number that resembles a quite high, because typically the numbers that normally we are acquainted of is about 1 to 3%. So any specific reason why these numbers came up so high when compared to the references?
Thank you for the question. In the case of stumps, it's because when the stumps are harvested from the soils, they have about 40 years of age, because they are only removed after the end of the revolution. So there will be an enrichment of extractives along the time. So that's why is the reason that they are they have a lot of extractives. For example, the eucalyptus wood that is used on the pulp industry, I think it's about 2-4%, so it's really low. And for stumps, if we remove first the extractives, it's solvents that in the pulp system are not going to be used to remove and degrade those extractives, and can target right away the lignin part. In the case of acacia biomass, we started recently focusing more on acacia biomass, and we are working with a lot of different species of acacia, 8. For example, in the afternoon, a guest will speak about acacia, 5 species of acacia potential to be used on pulp, and we are studying both wood and bark. And the case of the crown residues was only for melanoxylon, because bark, Sintra Mons da Lua, divides these residues on that.
Okay, so a follow-up question on that, just to finalize from my side with you. I think from the acacia also notice a slightly, well, not slightly, but actually an increase on the DCM extractives, so the non-polar type of extractors compared to the eucalyptus. And of course, within the industry is always talking about, eventually at some point using acacias as a raw material. Do you believe that when starting to introduce that material in the kraft pulping process, if that could be an issue in terms of higher amount of extractives that we can find on acacia, and if there's any species actually is better than eucalyptus?
So in the case of acacia, the higher amount of hydro-soluble in dichloromethane, that was your question, right? So it was mostly in the crown residues and mostly because of the leaves, as we've seen in the presentation of Professor Helena Pereira. So in the case of pulp, we would only be using the wood parts, and we saw that the wood chips from acacia were very similar to the composition of eucalyptus. If in the future we start using acacia for wood pulp, I don't know if it will be on the long term because we have a big problem with acacia invasiveness, but I would think it would be until we get lower and lower amounts of acacia available for the industry.
So coming back to the audience, I have one question to Dmitry here in my pocket. So if there's none additional questions, then I'll shoot to Dmitry. And again, very interesting work, a lot of work actually being done out there on a sulphite valorization for this ellagic acid and sitosterol. Making an analogy with the chemistry from the acid sulphite to the alkaline kraft. And we know there's differences in how these different pH ecosystems work with extractors on wood, where you see that the possibility to transpose these findings into the kraft alkaline pulping, where you see the streams that could actually be enriched on these type of components.
Thank you for the question. The thing is, I already mentioned in my presentation that the pH, and as you well said, plays a crucial role in this process. And actually in the alkaline extract, I mentioned earlier that is very important, the first neutralization to pH 7. And thus, I would say, depending, of course, on the process, the kraft process may be incompatible with some of the ways that I have proposed. However, it's not impossible. I never studied the process itself. However, I believe it is possible. It is possible. But the pH actually, because the process have many possible changes, especially in the context of industrial variability that you are well known of. And I would say that it's a matter of trying. However, in this case, for example, it's possible in the alkaline extract because of the components itself, because of the target component, the sitosterol. It has some properties, and again, maybe I didn't explain very well, because of this valorization again, the conjugated sterols. Even if this process has drastic conditions, how is it even possible that we have conjugated sterols and we could make a valorization of these products? And our initial hypothesis was that during the pulping process, there's microparticles that are formed, and simply these molecules are harbored from the reagents, and they are simply leached during the extraction stage. So once again, it's tackling these minor details in the process and trying to achieve, once again, the desired results on our target compounds. Thank you.
Okay, thank you again, everybody. If there's no additional questions from the audience, I would like to thank to the speakers, very nice presentations and very nice discussion as well around here. So round of applause to the guest speakers.